Okay, another fascinating concept. I've already given you some examples, and we've already seen a lot of heterogeneity in this course, actually. Heterogeneity is a fact of life. It's a way of enabling flexibility. If you want to be flexible, customizable, you need heterogeneity in the system. You cannot have everything to be the same. And this is true in nature, as we will see also. This is true in system design also. This is true in the way we use resources as human beings also, right? We have all these heterogeneous things, and there's no building that is one size fits all, right? Buildings are very heterogeneous, right? You specialize the buildings, you customize them. So it's a concept that's very, very common. Yet, when we're designing computers, sometimes we forget about these. So, but heterogeneity is the general concept that we will cover. But before we start, I guess I had the slide that I forgot about. So if you want to do research on top of this, if you really like these concepts or are excited about them, again, talk with me. I had this part earlier. We have a bunch of projects, bachelor's, semesters, masters, or if you have some idea, I'm very open to that also. Usually ideas are what drive really big innovations in the end. And these are some of the topics that my group works on. Memory, clearly, we've discussed a lot of that, and there's a lot more to do. I've actually given you a bunch of research directions while we are discussing these topics. Processing in memory, hardware security is a very important area, actually. There's an increasing effort in that, and there are a lot of things that need to be discovered over there. Reliability is another part that's not over here, but it's implicit. New computing paradigms, I think we need to discover new computing paradigms. We can discuss about that. We saw some of them, like processing in memory, but there's more. I think you've seen that I've been harping on some of this in some of the lectures, using machine learning for a good purpose for system design, which is an area that's wide open. That's, if you're interested in that, there's a lot to do in this area. And certainly genomics, system design for bioinformatics and health. So a lot of the topics we've covered and some of the topics we didn't cover. You can think of this as everything in computer architecture. And I'm actually very open to new ideas. It's not just top down, it's also bottom up, because it's really, sometimes the best ideas come from really bottom up. And you may have an idea that you may not even realize the importance of, and that idea grows somehow with the right inputs, and that makes a big difference. So that's really important to keep in mind also. So don't think of these as set in stone. There are a lot, in the end, research is a very unstructured entity. If you ever want to do research, it's really good to know that. It's a very unstructured thing. If you want to impose structure on it, you can destroy creativity. Too much structure. If you have very little structure, it may be good for a while, but sometimes you need some inputs to actually not fully impose structure, but guide how things are going. So it's good to develop a lot of ideas, basically. Okay, so don't think of this as a structured thing. There's a lot more to do in architecture. Okay, now that I've said that, let's talk about heterogeneous multicore and bottleneck acceleration. This is the goal for today and tomorrow. And these are some of the works. Some of them are really interesting. I already mentioned that to you. But the basic concept we're going to cover is heterogeneity. It's also called asymmetry. This is a concept that enables specialization, and they have the same meaning. Contrast this with homogeneity and symmetry. Everything is the same, basically. It's a very general system design concept and a life concept as well. The basic idea is, instead of having multiple instances of a resource to be the same, or homogeneous or symmetric, design some instances to be different, or maybe all instances to be different, right? They're all heterogeneous or asymmetric. Different instances can be optimized to be more efficient in executing different types of workloads, for example, or satisfying different requirements and goals. You may have different reliability requirements, and you may have different cores that provide you different reliability guarantees, right? Or performance or power. You can actually have this on every metric, and you have different combinations of the metrics. Of course, design space complexity grows if you do that. This enables specialization and customization, and if you understand your computation and what you're trying to do really well, you can map your pieces of computation to these different resources such that you maximize some metric or multiple metrics at the same time. So why do you want asymmetry in design? This is a limited view. This one's a very broad view, of course, but the limited view, different workloads executing in a system can have different behavior. And we've seen this many times, right? Different applications can have different behavior, different execution phases of an application can have different behavior. The same application executing at different times can have different behavior because your input set is different, right? And because of the dynamic events. Like when you're processing an image that's all black, that's different from an image that has a lot of changes in different parts of it, right? That's a very simple input set, but the behavior of the application differs a lot because of the function of the input set. So, and this affects many, many things that we've discussed. Locality, predictability of branches, instruction level parallelism, data dependencies that you have, serial fraction in a parallel program, how much can you parallelize, bottlenecks in the parallel portion of a program, as we will see, interference characteristics, and basically a lot of things over here. And also, so applications have different behavior, but systems are designed to satisfy different metrics at the same time. As we've been discussing, there's no single metric that you're optimizing for. Those days are done, actually. At some point, designs were mainly optimized for performance and the cost. But now we have actually n metrics that we're optimizing for. Especially in a system like this, for example, you're really optimizing for at least 5 major metrics. You can guess what those are. You can think about the 5. Okay, and there's almost never a single goal of design depending on the design point. And some of them are here, right? Performance, efficiency, fairness, predictability, reliability, availability, cost, ... Okay, so basically the problem is symmetric design is a design that's one size fits all. That's basically not adaptive to either of these, right? You have the symmetric resources. It tries to fit a single size design to all workloads and metrics. But it's very difficult to come up with a single design that satisfies all workloads, even for a single metric, actually. And we've seen this before, right? Clearly, if you design a general purpose processor, it's not going to satisfy all workloads. And also, it's very difficult to come up with a design that satisfies all different design metrics at the same time. And the things become even more difficult, of course, if workloads are changing, metrics are adapted to people's requirements. And this holds true for different system components or resources. Whatever we've looked at, cores, caches, memory, controllers, interconnect, disk, servers, this all holds true. And true for also software as well, algorithms, policies, and the software you design. So this is my pictorial view of symmetry versus asymmetry. Symmetry looks like this. Basically, everything is symmetric. Maybe it looks beautiful. But energy and performance, let's say 2 metrics, are suboptimal for different workload behaviors in this case. Basically, it's one size fits all. Asymmetry is, this is another example. This has some sort of asymmetry over here. You can imagine what these could be. It could be cores, it could be caches, it could be whatever resource that you can imagine. In this case, now you at least enable some choice, right? You can enable customization and adaptation. If the processing requirements vary across workloads, applications, and phases, you can pick which resources you execute the code on. And hopefully, you pick the right thing and you execute the code on both best fit resources to achieve minimal energy and adequate performance. So the concept at the conceptual level looks like this. But the designs we're going to examine will look kind of like this also. But of course, it's a much more general concept. And we've already seen examples of asymmetry or heterogeneity before in this course. And in also digital circuits. Actually, you first saw this in digital circuits. K1 design, it's a vector machine. It's a SIMD machine, but it's a heterogeneous machine, right? It basically has a vector pipeline, but it also has a scalar pipeline. In fact, when I teach SIMD, you know that Cray1 has the fastest scalar processor of its time. It's known as a SIMD processor or supercomputer at that time, but it has the fastest scalar processor of its time because there's a serial bottleneck, and you want to get rid of the serial bottleneck such that your parallel performance dominates your performance, right? Modern processors have scalar instructions plus SIMD extensions. We've seen decoupled access and execute. You have access and execute processors. They're specialized for different things. We've seen very recent examples. Thread cluster memory scheduling is based on the realization that different memory scheduling policies are better fit for different thread clusters. Again, asymmetry. Radar is an example of heterogeneity. You have heterogeneous refresh rates in DRAM as opposed to one-size-fits-all refresh rate. Heterogeneous latency DRAM, like tiered latency DRAM, and many other examples of the heterogeneous latency DRAM that we've seen. As opposed to having one-size-fits-all symmetric latencies, you just have asymmetric latencies for different portions. Hybrid memory systems is another example. That's almost a really good fit example that we've seen early on. You have these different asymmetric components, right? And you can actually, this doesn't end. You can imagine many, many different components. Of course, to be successful, you need to come up with a design that's actually improves some metric by a significant amount, right? Okay, we've seen examples of DRAM and phase change memory clearly, and reliable, costly DRAM and unreliable, cheap DRAM, for example. And heterogeneous cache replacement policies, we just talked about them, right? You have a lot of heterogeneity. As opposed to having a single replacement policy for all blocks, have very heterogeneous replacement policies for different blocks based on their behavior. So examples abound everywhere, and systems are becoming increasingly more heterogeneous. And I don't even put the CPUs, GPUs over here, right? The accelerators, that's old compared to some of these over here. Okay, this was an example, asymmetric design. I like putting it over here because it's one of the first examples that you've been introduced to perhaps in the design of machines. So you have these vector registers, vector part of the machine, and a scalar part of the machine. And scalar part was much faster than any other scalar machine of its time, as we've discussed before. Hybrid memory systems, again, heterogeneous by definition. This is thread cluster memory scheduling, and you can see heterogeneous policies over here, and we already discussed these. So this is just to jog your memory. Heterogeneous refresh rates, exploiting the heterogeneous retention times. So this is one example where heterogeneity actually can come from underlying conditions, right? Underlying system has heterogeneous retention times in this case, but it's not exploited today, right? Today everything is refreshed every 64 milliseconds, but if you actually expose that to the memory controller and exploit that, you can have a heterogeneous refresh rate based system that's exploiting the heterogeneous behavior that's underlying. So I'm pointing this out because you may actually have underlying heterogeneity given to you almost. The system, because of process variation, is already heterogeneous, and you just need to exploit it. Or you design the system to be heterogeneous. You create heterogeneity, architect heterogeneity inside the system. These are two different cases. Because of process variation, you have these refresh rates. As a result, you exploit it. This is already given to you. This is an easy case, perhaps, right? Assuming you can actually exploit it. Maybe a harder case, architecting the system to be heterogeneous, right? So I don't fully know exactly how to do this, but you could imagine maybe designing some of the DRAM cells to be high retention and some of the other DRAM cells to be low retention, and architect it that way as opposed to being at the mercy of process variation to exploit things. Okay, so this is another example. The tiered latency DRAM is a very good example of heterogeneity. Here you're trying to balance two metrics, area versus latency, and we created heterogeneity, if you remember. And whenever you have an example that looks like this, you have one design choice that's green at one thing, that's red at some other thing, another design choice that's green at some other thing and red at some other thing, then maybe heterogeneity is a good solution, right? You basically try to get the greens as much as possible while avoiding the reds as much as possible. If you do something right in the system, in this case, the something is data mapping, right? And deciding where to put what is the right thing. In other cases, it may be scheduling, as we will see in the full lecture. So we've already seen many examples, but it's always good to spot these and build heterogeneity into the systems. Okay, and so this is something that we haven't examined. After we talk about interconnects, you will appreciate this even more. For example, this is one commercial design. It was the Tylera design. I'm not sure how it's doing right now, but it was one of the very simple, large-scale multi-cores of its time. It has a 64-core machine. It had a 100-core machine. There's an example over here, the 3x3 array. And it had these two-dimensional mesh networks. And you can say, oh, two-dimensional mesh network. You just build one, it's good, right? But it's not good. You need heterogeneity in that mesh network. It had actually 5 networks on chip interconnects. 4 of them were packet switched. 1 of them was circuit switched. As we will see, circuit switching, you need to set up the route before you start sending packets. And things go smoothly from source to destination after you set up the route. Packet switching means every router needs to make a decision based on the packet. So it's very dynamic, where this is, after you set up the route, it's pretty static. You don't do any routing after you set up the routes. So these are different types of networks, as you can see. And different types of data or communication patterns are fit for these different types of networks. For example, in the circuit switch network, I think it's called streaming transfer network. In this case, that's what STN stands for. Well, I just made it up. It's called static network over here. But it makes sense for streaming data. That's why I made it up, perhaps. Basically, usually circuit switching is very good for streaming data because you're doing bulk transfers from this node to this node, and you don't want to pay the overhead of dynamic switching in each router. You set up the circuit, and all of the routers route the message to the destination that's set up. It's very powerful, very low overhead, low latency, high bandwidth. And you design this network so that you can handle these streaming data transfers. So for example, if you're copying data from this node to this node over here, you use the streaming network or circuit switch network. And there are other 4 networks over here. For example, cache request packets go through this TDN, tile dynamic network. They didn't choose great names. Basically, it's dynamic because it's packet switched, I assume. Yes. And basically, cache requests go through that network. Cache responses, so if this core wants to access this cache slice over here, it sends requests to this particular network optimized for that. If the response, and the requests are small, so these are small packets, because you're not sending any data, you're sending a request. I want to read, or I want to write. And then you're sending the data on this memory dynamic network, data network essentially. And these are big packets. So the reason the networks are different is because they're specializing for the data sizes that are transferred on the network. There are also other reasons that we will discuss in the interconnect lecture to prevent deadlocks in the networks is another reason why you would like to design multiple networks. I/O packets go through some other network, and core-to-core messaging that's not streaming goes through some other network, as you see over here. So even something that's as simple as a 2-dimensional mesh is heterogeneous to cater to the needs of different types of data and communication that's transferred on them. And that's not heterogeneous enough. There are many more other proposals that make the network even more heterogeneous. But we will discuss that when we get to networks. So, I mean, this is a very fundamental principle. Heterogeneity is abundant in life also, both in nature and human-made components. We've seen buildings, for example. Humans are heterogeneous, right? All of us are heterogeneous here. Even identical twins are heterogeneous in some way. Yeah, they're the closest to the homogeneous probably. Cells are heterogeneous. They're specialized for different tasks. Organs are heterogeneous. Cars are heterogeneous. Okay, I'm not going to go through this more. So homogeneous design actually makes no sense if you think about all of this. Right? We should also discuss this. Asymmetry or heterogeneity is actually a way of enabling specialization. There's this general purpose versus special purpose that we've been discussing. Heterogeneity is really, if you want to enable specialization, you have to have heterogeneity. Basically, by having heterogeneity, you bridge the gap between purely general purpose and purely special purpose. Purely special purpose is something that's completely designed for a single task, and you can only do that task. Right? It's not very programmable. Basically, you design an ASIC that does, speech processing only. And it requires speech to be input and something as output. Maybe it translates the speech to text, for example. It's not very programmable, or it's a very limited programmability. But if you actually have heterogeneity of different forms, you can bridge the gap between a programmable, very programmable general purpose engine and not so programmable special purpose engine. And whenever you go from general purpose to special purpose, you lose ease of programming, but you gain a lot in efficiency in terms of performance as well. So purely general purpose, single design for every workload or metric, highly programmable. Purely special purpose, single design per workload or metric, not so programmable. And there are shades of gray, of course, in between these, and you can construct different levels of heterogeneity. Asymmetric, or some version of asymmetric, is you can have multiple sub-designs optimized for sets of workloads or metrics and glued together. Maybe you can have different types of cores that are getting special purpose, but not as special purpose, still programmable. GPUs may be a good example of this, by the way. And the CPUs that are good for many workloads. That's an example of heterogeneity, right? CPUs versus GPUs. GPUs are not the extreme special purpose engines. It's not doing just one task, right? They're doing many, many tasks, actually. And they're becoming increasingly less special purpose. Okay, so the goal of a good asymmetric design is really to get the best of both general purpose and special purpose. It's another way of looking at a heterogeneous design. You basically want to get the best of both worlds. Okay, so let's look at the overall high-level advantages and disadvantages. So the big advantage of symmetric design, I've already given you the motivation, so the motivation is very similar to the advantages. So you can enable optimization of multiple metrics right now. You can enable better adaptation to the workload behavior. You can provide special purpose benefits with general purpose usability and flexibility, hopefully. You lose something, of course. The disadvantages are usually you have higher overhead and more complexity in design and verification because essentially you don't have a single component that's homogeneous and you design it and verify it and you just replicate it. That's a lot easier, clearly, right? But if you want to do something better, you need to pay the cost of higher overhead and more complexity in design and verification. Higher overhead in management, there's also management complexity because now you have a choice. You need to decide where to execute what data to map where, and that leads to issues like scheduling, data mapping. So clearly you pay the cost of management complexity also. Whereas if you have all homogeneous cores, you don't have that cost, right? Every core is the same. As a result, you don't have that choice. You don't need to have that management complexity. And there's also overhead in switching. If you want to change your decision, you need to switch between multiple components, and that can lead to degradation in terms of the metric that you're trying to optimize for. This is true for symmetric also. If you have symmetric components, if you want to switch from one component to another component, if you have state, clearly you need to migrate the state somehow. That leads to overhead, but it could be even higher in asymmetric components. Because they may not be very good. The state may be very large in one, very small in another one, right? So this is another example over here, as we've discussed. We integrate multiple general purpose cores and multiple GPUs together, CPU-GPU systems. And interestingly, they're not just heterogeneous in terms of some metric, but they're also heterogeneous in terms of their execution models, right? CPUs are single-threaded or multi-threaded, whereas GPUs are SIMD execution model. So it's completely different programming models that you use to program them. So heterogeneity exists not only in architecture, microarchitecture, or devices, but also at the very, very higher levels in execution models. So some of the things that we're covering in this lecture have been the memory system, efficiency, performance, energy, and scalability, predictability, and robustness. We've done actually a lot in these. I'm not going to go through this in detail. You can read this by itself. But basically, a lot of the things that we've looked at in memory system and predictability and robustness so far, we've actually come up with a lot of asymmetric solutions. Maybe we didn't call it asymmetry at the time. Sometimes we did call it asymmetry. But asymmetric designs are actually very good at solving the problems that we're facing in the future or currently. We haven't looked at this aspect as much, except within the context of memory system and predictability and robustness. Basically, if you improve your efficiency broadly viewed as performance and energy, you can improve your scalability, and you can enable scalable systems that can enable new applications, and you can enable better user experience, which can enable new usage models. So this aspect we have not looked at as much, but asymmetry actually can be very useful in this aspect also. And in the next lecture, actually, we're going to cover those aspects. But these are some other examples of commercial asymmetric design examples. These already exist: CPUs, GPUs, CPUs plus hardware accelerator. Your cell phone is a great example of asymmetry. Even in the processors, ARM's big little processor and IBM cell processor was one of the earliest examples, as we've discussed. It's basically a heterogeneous multi-core engine where you have one control core and a bunch of other cores, but there's no cache coherence in it. We've discussed that, and it was a nightmare to program. And if you look at this picture over here, there's increasing asymmetry in all of the components over here, as you see. So I think I'm done with the philosophy and motivation and the importance of asymmetry. And we don't have time left, so in the next lecture tomorrow, we'll talk about multi-core design, especially focusing on the cores, and how we can use asymmetry to make things much more efficient and much more scalable. Okay, so that's right on time, and I'll see you tomorrow.